we're now going to take a look at vertical asymptotes. Now, vertical asymptotes occur wherever a function has an infinite limit. And it's important to consider these because they represent where a function has some type of strange behavior. It's breaking up to positive infinity or down to negative infinity. So if we want to understand the behavior of a function and what its graph looks like, then we need to identify where it has these vertical asymptotes. So let's start with the definition. So if the limit as x approaches c from the right of f of x is positive or negative infinity, or the limit as x approaches c from the left of f of x is positive or negative infinity, then we say that f of x has a vertical asymptote at x equaling c. Now note that vertical asymptotes are normally denoted as a dashed line in the graph of a function, even though that dashed line is not part of the graph of the function. It's just used as a guideline to indicate where the vertical asymptote is occurring. Now for all of our problems that we're going to consider, our vertical asymptotes are going to take one of the following forms. They're going to look like either this one, where we see that as x approaches c from the left, our function breaks down to negative infinity, and as x approaches c from the right, our function breaks up to positive infinity. And so then we have these left and right hand and full limits down here. The right hand limit is infinity, left hand limit is negative infinity. The full limit, we say, does not exist. Alright. Now notice that these limits, technically, they are also not existing. These also do not exist, but we're specifying the type of DNE that they are. You could also have one that looks like this. The function could break up to positive infinity as x approaches c from the left, and down to negative infinity as x approaches c from the right, in which case you would have these results for your right, left, and full limits. It could also break upward on both sides of c. As you approach c from the left and the right, the function breaks upward on both sides, in which case you have your left, right, and full limits all equaling infinity. Or the function could break down to negative infinity as x approaches c from the left and the right, in which case your right, left, and full limits are all negative infinities. Now let's take a look at a quick way to determine when an asymptote exists at a point C. So if we're given a function of this form, if we're given a function of the form f of x divided by g of x, where we're going to assume f and g are continuous functions, which mostly all of our functions are, then vertical asymptotes can be found by solving for where the denominator is equal to 0. You solve those for the values x equaling c, and then you use the following rule to determine if x equaling c is a vertical asymptote, or if it requires more analysis, it might not be a vertical asymptote. Alright, so you solve for where the denominator is equal to 0, you get a bunch of values, several values, and then you can use the following two results to determine if those values are vertical asymptotes or not. Number one, you evaluate f of c divided by g of c. If you get a value back like m divided by 0, where m is a non-zero number, so if you get back something like 5 divided by 0, then your function will definitely have a vertical asymptote at x equaling c. On the other hand, if you evaluate f of c divided by g of c, and you get 0 divided by 0, then your function f over g, it may or may not have a vertical asymptote at x equaling c. So you have to do more analysis on the limit as x approaches c of your function. You may need to use the cancellation or rationalization technique, and if when you use those techniques you get back a number, then you would not have a vertical asymptote. All right, so let's take a look at a few examples to better clarify this. So our first example here, we're given the function 1 divided by x squared minus 1. We want to find all the vertical asymptotes and identify the right and left hand and full limit behavior near those vertical asymptotes. Okay. So the first thing we want to do is we want to find where the denominator is equal to 0. So we're going to set that equal to 0. Now let's notice that that actually factors as and then when we set that equal to 0, we get x equals plus and minus 1, 1 and negative 1. Now let's see if these are vertical asymptotes or not. Well, because our numerator is 1, it's pretty clear that these are going to be vertical asymptotes, but let's go through the test anyway. If x is equal to 1, notice that if I put 1 in for x into the function, notice I get that f of 1 gives me back 1 over 0. Alright, right away 1 is a vertical asymptote. So we'll list our vertical asymptotes over here. So we know that x equals 1 is definitely a vertical asymptote. Now let's identify this right, left, and full limiting behavior. So let's take a look at the right-hand limit. So if we look at the limit, alright, so now as x is approaching 1 from the right, that means that x is going to be taking on values like 1.1, 1.01, 1.001, and so on. So you can see that the denominator, if I plug numbers like this into the denominator, I'm going to get back a small positive number, because 1.1 squared is going to be a little bigger than 1. So the denominator is going to be approaching 0 from the right. The numerator, well, that's always approaching 1. So this is a positive number over a very small positive number. So my function is behaving like 1 over very small positive number. That is infinity. Okay, so this limit is positive infinity. Now let's take a look at the limit from the left. Well, let's see. So if x is approaching 1 from the left, that means it's going to be taking on values like 0.9, 0.99, and so on. If I plug 0.9 in here, 0.9 squared minus 0.9 squared is definitely going to be less than 1. So this is going to be a negative number. It's going to be a small negative number. So we see that this is approaching 0 from the left. The top is always approaching 1. And so this is behaving like 1 divided by a very small negative number, which is going to negative infinity. So we can say that this is equal to negative infinity. Alright, so that's our right, left-hand limits. Now let's take a look at, let's see, what's the full limit going to be? Well, the full limit we're just going to have to say that the full limit does not exist, right? Because we have two different infinities for our right and left-hand limits. If they were the same infinity, we could put that infinity over here. But so we're left saying it does not exist. Now let's look at x equals negative 1. Well, of course, if I put negative 1 into the function up here, notice you get back 1 over 0, of course, again. Well, because I have a non-zero number in the numerator, 0 in the denominator, this is definitely going to be a vertical asymptote. So there are both of our vertical asymptotes. We've identified them. Let's identify the limiting behavior near those asymptotes. So if I look at the limit, as x approaches -1 from the right, now if x is approaching -1 from the right, that means it's going to be taking on values like -0.9. You have to be careful here. Okay, -0.9 is to the right of -1. It's a little bigger than -1. Then this is going to be a small negative number, because if I put -0.9 in here for x, that's going to be less than 1, so this is going to be negative. So this is approaching 0 from the left. The top is always approaching 1, and so our limit, well, I'm looking at 1 divided by a very small negative number. That's going to be a very large negative number. Limit as x approaches -1 from the left. Well, as x is approaching -1 from the left, it's going to be taking on values like -1.1. Now if I put -1.1 in for x squared, that's going to be a positive number, and it's going to be a little bigger than 1. So this is going to be a small positive number now. So this is approaching 0 from the right. This is still approaching 1. 1 divided by a very small positive number is going to be a very large positive number. So there's our limit. And then the full limit we're just going to have to say that that does not exist. All right, because our left and right hand limits are a different type of infinity. Okay, let's see if all of this matches up with what the graph of the function actually looks like. So I'm going to bring that up here. I'll leave it down here. So here's what the graph of the actual function looks like. Right here is -1. Right here is +1. Notice as we approach -1 from the left, the function is going to positive infinity. Let's see. -1 from the left, positive infinity. Yeah, that's what we found right there. As we're approaching -1 from the right, the function is breaking down to negative infinity. Let's see. -1 from the right, negative infinity. Yep, that's what we found. As we're approaching 1 from the +1 from the left, going down to negative infinity. +1 from the left, negative infinity. As x approaches +1 from the right, it's going up to positive infinity. +1 from the right, positive infinity. Okay. And notice the dashed lines indicating our vertical asymptotes that we found. All right, so that's how we do that one. Let's take a look at another one. So for this function, x squared minus 9 over x squared minus 5x plus 6, we want to find the location of all of our vertical asymptotes and identify the right, left, and full limits near those vertical asymptotes. So for this function, let's notice first of all that we can do some factoring, right? We can write that as and notice that the x minus 3's will cancel. So what happens now is we see that 3 is not going to be a vertical asymptote for this function. You know, if we were to solve for where the denominator is equal to 0 here, you see we'd get back 3 and 2. But 3 is not going to be a vertical asymptote because we have cancellation. In other words, the limit as x approaches 3 of this function is going to be 3 plus 3, 6, divided by 1. That is a number. It's not a positive or negative infinity. So 3 is not a vertical asymptote for this function. Now, of course, if we set x minus 2 equal to 0, of course we get back x equaling 2. And that is going to be our vertical asymptote. Oops. And let's analyze it a little bit further. Let's in particular note that when x is 2, if I look at f of 2, let's just really verify it as a vertical asymptote using the rule we had above. Well, if I put 2 into the function, the original function, notice that I get back negative 5 divided by 0. And so since negative 5 is a non-zero number, 2 is definitely a vertical asymptote. Now let's take a look at the right, left, and full limiting behavior near 2. So if we look at the limit, now since I canceled the x minus 3's, I can really just consider x plus 3 over x minus 2. It would be okay to leave those in, but we don't need to. It's a little easier if they're not there. So now notice as x approaches 2 from the right, x is going to be taking on values like 2.1. So the numerator is approaching 5. The denominator is approaching 0 from the right side, right? Because if I put 2.1 in here, I'm going to get a small positive number in the denominator. 5 divided by a very small positive number is going to be a very large positive number. So positive infinity. Limit as x approaches 2 from the left, x plus 3. Now as x is approaching 2 from the left, it's going to be taking on values like 1.9, 1.99, and so on. The top is still approaching positive 5. The denominator, however, is now approaching 0 from the left, because if I put 1.9 in for x, I'm going to get back negative 0.1. That's a small negative number. 5 divided by a very small negative number, a very large negative number, negative infinity. All right, so there's our right and left hand limits. The full limit then of our function, we're just going to have to say that that does not exist, because we have different types of infinity here. All right, so there's our behavior of the function near the asymptote. Let's see if it matches up with what our graph says. So here's our graph. Right here's 2 on the x-axis. Notice as we approach 2 from the left, our function is going down to negative infinity. And let's see, 2 from the left, negative infinity. Yep, that's what we have. As we approach 2 from the right, our function is breaking upward towards positive infinity. Let's see, 2 from the right, positive infinity. That's exactly what we found. Okay, so our graph does match up. The only thing our graph doesn't really pick up here is at x equaling 3. Let me just point this out. Right at x equaling 3, right here, we should really have a little open circle right there, because the function is technically not defined at x equaling 3. Because if I put 3 into that function, I would get back 0 divided by 0. That's undefined. Now, if you were to type that function into your calculator, you would not see that little open circle. Your function won't give that back to you because it's so tiny, it normally just skips right over it. So you wouldn't see it, but it should be there. All right, let's take a look at one more problem. All right, so here's our function. We're going to find all the vertical asymptotes for this one. So let's take our denominator here and factor it. We can't do anything with the sign. So we have x cubed plus 2x squared and now setting that equal to 0, we get that x equals 0, -4, and 2. So these are where we have possible vertical asymptotes. So let's take a look at 0 first. Notice if we put 0 back into the function, we get the sign of 0 is 0, and the denominator, well, that's also 0, because if I put 0 in right here, that's going to knock everything else out. I'm getting 0. 0 may not be a vertical asymptote. Let's take a look at the limit as x approaches 0 for this function and note this. So what I've done here is I've just broken this up a little bit. Notice I still have my sine x in the numerator if I multiply through, and in the denominator I just have the factored version of x cubed plus 2x squared minus 8x. Now as x goes to 0, this term right here, the sine x over x, well, that's one of our favorite trig limits. That's 1, right? That's approaching 1. This term right here, as x approaches 0, I'm getting 1 over 4 times -2. That's approaching -1/8. And so this limit is -1/8. So 0 is not a vertical asymptote. The limit actually exists. All right. Well, let's take a look at the other ones. What about x equaling -4? Well, if we plug -4 in for x into the function, we get the sine of -4 divided by 0. And, well, if the sign of -4 is actually a non-zero number, if you put it into your calculator, you'll get something back like 0.9 divided by 0. And, of course, then that tells us that -4 is definitely a vertical asymptote. Let's see, we'll just keep track of our vertical asymptotes up here. So x equals -4, that is definitely a vertical asymptote. Now, what about x equaling 2? Same thing. If I evaluate f of 2, we get back the sine of 2 divided by 0, because when I put 2 in here, x minus 2 is a factor of this, so right here it's going to make it 0. And now the sine of 2 is about 0.76. It's a non-zero number. That's what's important. And so that indicates that 2 is definitely going to be a vertical asymptote as well. Now let's look at the graph of the function to see if it matches up with what we found for our vertical asymptotes. If we look down here at the graph, yeah, right here, we see that we have a vertical asymptote at -4, another one at 2. Notice our function does not indicate any type of asymptotic behavior at 0. We saw that that was not a vertical asymptote. Our limit was actually -1/8. That's right here on the y-axis, -1/8 right there. We should actually have a little open circle right there in our graph because technically it's not defined at 0. All right. And yeah, everything matches up with what we found. Now, if we did want to find, the right and left hand limits without looking at the graph, you would just have to do what we did above. I'll just do one of those quickly, like with x equaling 2. If you wanted to look at the limit as x approaches 2, let's say from the right, let's verify that it's positive infinity. We would look at our function, which was sine x divided by, and I'm going to put here the factored version of our denominator. And what you would think of, okay, x is approaching 2 from the right, it's a number like 2.1. The sine is, the top is approaching the sine of 2.1, or 2 rather, sine of 2, which is approximately 0.76. It's a positive number, that's what's important. The denominator, what's it doing? Well, x is approaching a positive number 2. X plus 4 would be approaching 6. X minus 2 would be approaching 0 from the right. It would be a small positive number. So positive number times a small positive number, the bottom is approaching 0 from the right. So you have a positive number divided by a very small positive number, that's almost 0. That's going to be a very large positive number, infinity. And that's exactly what our graph indicates over here. Same thing for the limit as x approaches 2 from the left. You would have the top would still be approaching 0.76. This would still be approaching 2 and 6, but this term would be approaching 0 from the left because I would put a number like 1.9 in for x. This is negative. The whole bottom term is approaching 0 from the left. This is negative infinity. A positive number divided by a very small negative number, very large negative number, and we see that behavior from the graph over here. Alright. Okay, so that does it for these examples. Let's take a look at one last theorem. So for this theorem, we are letting C and L be two real numbers. We have two functions, f of x and g of x, in which the limit as x approaches c of f of x is infinity, and the limit as x approaches c of g is L. Then we have these three results. The first one states that the limit as x approaches c of f of x plus g of x is going to be infinity. That makes sense because if f of x is approaching infinity and g of x is approaching some number like, whatever, 5 or so, of course a really, really large number plus 5 is going to be a really huge number. In other words, infinity plus 5 is infinity. So that result makes sense. Number 2 makes a statement that the limit as x approaches c of f times g is going to be, two cases here, is going to be infinity if L is positive, and negative infinity if L is negative. That makes sense also because if f is approaching infinity and g is approaching a number like 5, then, 5 times a really large number is going to be a really large number. In other words, 5 times infinity is infinity. If, on the other hand, g were approaching a negative number, such as negative 5, then negative 5 times infinity would be a really, really large negative number. So negative 5 times infinity is negative infinity. So that makes sense. Number 3 says that the limit as x approaches c of g of x divided by f of x is going to be 0. So suppose, for example, g is approaching the number, L, which, say 5, just for example, and f of x is approaching infinity, well, a number like 5 divided by a really huge number is going to be a really small number. So this is approaching 0, right? No. Okay, so that result makes sense also. Let's take a look at a few examples where we use these. So for the first one, we're taking a look at the limit as x approaches 2, x squared plus 1 over x minus 2 squared. So we have two limits here to consider. Limit as x approaches 2 of x squared, and limit as x approaches 2 of 1 over x minus 2 squared. Alright, of course this one is going to be 4. And this one down here is going to be positive infinity. And that's because as x approaches 2, x minus 2 is going to be a very small number, very close to 0. And then when you square it, that's going to make it a very small positive number. Whether or not x minus 2 is positive or negative, the square is going to make it positive. So this is approaching 0 from the right. The top is always staying at 1. 1 divided by a very, very small positive number is a very large number. It's approaching infinity. Alright, so what we have then is the x squared portion here. That's approaching 4. This portion right here is approaching infinity. So you can think of, from result number 1 up here, infinity plus 4, well, that's going to be positive infinity. Alright, so that's our answer, and that's how we reason it. Down here is the graph of what the function looks like. Notice that as we approach 2 from the left or from the right, notice how the function does indeed break up to positive infinity on the left and positive infinity on the right. So the full limit is positive infinity for this particular function, and that's what the graph indicates. Let's take a look at this one. So here we have limit as x approaches pi of the sine of x minus pi divided by x minus pi cubed. Now let's, well, funny here. Let's rewrite this as follows. We're going to try to rewrite it as two functions, one of which approaches a number and the other one approaches either positive or negative infinity. Well, let's write it like this. Oops. Let's write it as the limit x approaches pi Alright, so what we can see now, as x approaches pi, this piece right here is going to be approaching 1. That's going to be approaching 1, right? That's from the result of, that looks like a sine of u over u, and u is approaching 0 as x approaches pi, x minus pi approaches 0. So it's behaving like sine u over u, where u goes to 0. We know that that limit is 1. Over here, this limit, this one is also going to be going to, well, is going to be going to positive infinity. And that's because the denominator is approaching 0 from the right, and the numerator is approaching 1. So of course 1 divided by a very small positive number, very large positive number. And so what we have then, by result number 2, this is like our L that's being referred to in the theorem. 1 times infinity is going to be infinity. And so that's our answer. So the limit of this function as x approaches pi is positive infinity. And down here we have the graph of what the function looks like, and we can see that as x approaches pi from the left and from the right, the function is indeed breaking upward towards positive infinity on either side. All right, so that concludes this lesson on vertical asymptotes.